Okay, this is our menu for today. First, we're gonna talk about the Doppler effect, which is the situation where the frequency that you hear changes depending on how you move relative to the wave source, and also if the wave source itself move, then how will that affect the frequency perception of the detector. So that's going to be the Doppler effect. And then we're going to start talking about one very interesting and important effect of wave, which is interference. And that's going to lead to a few conceptual things like path difference, how standing wave is formed. And that's pretty much going to be what we talk about today. Before we continue, let's review a little bit what we did last time. So last time we actually did quite a few things. All right. So one thing that we did last time is the uh, intensity of sound wave. Right. So we define what it is. So the intensity is the power, and this power is the power of the source. So it's the total power radiated, let's say, from a speaker or from, a light source if we talk about electromagnetic wave. And then divide by the area. And this area is the area which kind of, enclose the, the wave source. For example, if we have, um, a light bulb which give out light in every direction, and we need an area, right, to calculate the intensity. So the area that we're going to use, in this case, the easiest is probably a spherical area around it, right? So it's a spherical shell. This is the area that we're going to put in here. And if you are distance r away from the source, then the area will be 4 pi r square. And the reason why we like to use this spherical area is because it's the same distance from any point of the surface to the source. So it's r here. This is also r, right? So we are sure that the wave amplitude at every point on the surface, no matter where you are, it's going to be the same. Okay, so that's going to be very convenient because you don't need to worry about, let's say you take a surface which looks something like this, then this will be far away from the source, where the point here will be close to the source. So you're going to have different wave amplitude on the surface of this. And that's going to make calculating the intensity a little bit harder, right? So we don't need to do that. So we're going to choose almost always a spherical surface like this, right? So in that case, you're going to have the intensity equal to power, which is the power of the wave source, divided by 4 pi r square. So because of this, you're going to have the inverse proportionality of 1 of r square. So the further away you are, the lower the intensity of the wave that you're going to receive. And that's something that you all expect, right? Because if you're far away from the speaker, then you're going to hear the sound a little bit softer. And this is the reason, because the energy of the wave is, it's kind of spread out through a larger area, so the intensity is lower, right? So you have larger area, so you divide by something more here, so the intensity is lower. And intensity of sound is related to what we call the loudness. And we talk about the reason behind this is just a mathematical tool to make dealing with very large number and very small number a little bit easier. And again, it's not something that introduce new physical concept. It's just, again, a mathematical tool. So that's the other thing that we talked about last time, right? So the loudness in decibel, which we use beta as a symbol for that. So it's defined to be 10 times log base 10, logarithm base 10 of the intensity of any point that you want to calculate. And then you need to divide by some reference intensity, which we call I min or IREF, sometimes called IREF. But it's just a fixed intensity that we can use because what we are doing here, we are comparing the intensity that we want to measure, our intensity I here, to some kind of reference. Okay, so that's what we are doing here. So in this case, I reference, we're gonna use 1 times 10 to the minus 12 watt per meter square. And this is kind of the lowest intensity that people can hear. Anything softer than this, your ear is not gonna notice. But I mean, some other animal might be able to pick it up. But we are talking about, like human perception of sound. So we're gonna use this number here. Okay. So from this, you can calculate the decibel value, which we call beta. So you have to do the logarithm of this. Okay, so this is what we talked about last time. And we are not done yet with kind of like the general, property of sound wave. So next thing we're going to talk about the Doppler effect. But the Doppler effect is actually not just applicable to sound wave. It's actually for it's true for any wave, but sound is probably the easiest to observe because we encounter this kind of effect in everyday life. All right, so let's talk about that. So that's going to be the starting of today's topic. Okay, so the Doppler effect. Okay, so Doppler is the name of a physicist. So what is the Doppler effect? Well, it's actually not really like a definition of what it is. It's just an observation, and we are trying to explain why that's the case. So people have noticed that there's a change in the frequency of sound, whether you move relative to the source or the source move relative to you. Right? So in general, it's the effect that describe the change in the apparent frequency, which just means the frequency that you hear, okay, when the source of the wave and also, so I put an or here, or the observer are moving. Okay, so that's both the source and the observer. So if you can move, both of them can move, or only one of them moves, it's going to change the apparent frequency, which is the frequency that you hear. Okay, so that's what we are interested in. Okay, so and that's something that you experience in real life, because like if you stand like next to a road, and then there's an ambulance coming in towards you, or hopefully nothing related to you, but you hear the siren of the ambulance. When the ambulance approaches you, you're going to hear the frequency of sound is getting higher and higher. And then when it goes past you, then the frequency will be lower. Okay. And if you look at, a video clip of, like a car racing, and you hear the sound, the sound of the engine, that's also the same thing, right? So I hope you all know what I'm talking about here. So let's try to explain why that's the case. So we're gonna look at one of the two cases at one time, so one at a time, okay? And then in the end, you can just combine. So the first case we're gonna look at is when the source is moving. Source is moving. Okay. So let's say you have an ambulance, and the ambulance we call the source. Okay, so this is the source because this is the one that is giving out sound wave. So let's say the ambulance is moving to the right with velocity given by Vs. Okay, so subscript S does not mean the speed of sound is the speed of source. Okay, the speed of sound will use just V. Okay, so let me write it here. So V is the speed of sound. And again, the speed of sound is determined by what kind of medium that we have here. In this case, it's just air, so you can assume that the speed of sound is probably 330 or something meters per second. Okay, so we're gonna have V, the speed of sound, and Vs, which is the speed of the source. Okay, and then we assume that the source is moving to the right. And then you have an observer, which may be yourself, standing here. And the question is, what frequency of sound that you're going to hear? Okay, so let's put in one important frequency, which is called F0. And F0 is the frequency that is observed, meaning that it's the frequency that you hear when Vs is equal to 0. So what does it mean? It means the regular frequency, the normal frequency that you're going to hear if nothing moves. So it's just, there's no Doppler effect in that case. Okay, so if Vs is equal to 0, the source is not moving, the observer is also not moving. Then what the observer here is going to be F0. Okay, so that's what we have here. Now let's talk about the case where Vs is not 0. Okay, so what happens if the source start to move? Then the observer gonna hear the new frequency f prime. Okay, so f prime is the frequency that is observed when Vs is not equal to 0. And that's what we are trying to find, this f prime here. Okay, so how do we do that? Well, if we if we try to draw, the wave which is coming out from the source, so the wave is gonna come out maybe like this, right? So if you draw the wave coming out, let's say you pick just one section here. When Vs is equal to 0, the source is not moving, then the wave will probably look like this. Okay, and I'm drawing just one section of the wave, so it should be clear to you that this is the wavelength of the wave. Okay, so if you draw the wave like this, then when it's not moving, then it's just a regular, frequency and regular wavelength, right? So lambda is related to f0 and related to the speed of sound, right? But now, if you start to move also to the right. Okay, so what happened is that you are compressing the wavelength to be something smaller. So when Vs is not equal to 0, right? So when the source is giving out wave, the source is also moving, right? So in the end, what's gonna happen is that by the end of one cycle of the wave, the source gonna move this much, and then the wave coming out will get compressed like this. So you can see what happened here is that it makes the wavelength actually shorter than it used to be. Okay, because the source is moving when it's giving out wave. So it's kind of like helping the wave to move, something like that, if that kind of picture helps. But you have to understand that the movement of the source gonna make the wavelength shorter. So the wavelength, instead of this whole thing, now it becomes just this, right? So it's shorter. So I'm gonna write is lambda prime, just to be the wavelength here, right? So lambda prime is shorter than lambda. And what is this distance here? Well, this distance here is how much the distance move, how much the source move after one cycle of the wave. Right. So this one is going to be Vs times some time here, big T. Okay. What is big T? Well, how long does it take to give out wave for one cycle? Well, that's the period of the wave, right? So if we combine these two pictures together, then what we're going to have is the lambda of the O wave, right, which is this thing, is equal to Vs times T plus lambda prime, using the picture that we have here, plus lambda prime, like this. Okay, so, and then what is big T? Well, big T is the frequency, 1 over the frequency. So Vs times big T becomes Vf divided by F0 plus lambda prime. Because by definition, the period of the wave is 1 over F0. Okay, so the source is always giving out the same frequency F0. Okay, so there's no change in the frequency. The observer might hear something differently, but it has nothing to do with the actual frequency that the source is giving out, right? So the period of the wave is always 1 over F0, even though the source is moving. Okay, so that means, well, lambda prime is the wave which combine the effect of the movement of the source. So that's going to be the lambda that the observer going to observe, right? So lambda prime then can be written in terms of lambda minus Vs over F0 like this. Okay, so this thing here is the observed wavelength. So you can see that it's kind of consistent with what we are using for the frequency, right? So you can either talk about the observed wavelength or the observed frequency like this. So if we have the observed wavelength, then how do you convert this to the observed frequency? Well, we know how they are related. It's V equal to F times lambda, right? So I'm going to go to the next page, right? So because v, which is the velocity of sound, is equal to f prime times lambda prime, right? So f prime then is simply v divided by lambda prime, like this. Okay, so lambda prime is what we had in the previous page. So I'm gonna just copy it here. So lambda prime is lambda minus Vs divided by F0. Okay, so for those of you who kind of a little bit lost, right? Lambda prime is this one, is the observed wavelength by the observer here. Okay, and I'm trying to use this to find what is the frequency, right? So knowing the wavelength, then you can find the frequency by doing f equal to v over lambda prime, f prime equal to v over lambda prime. Okay, and then we can substitute lambda prime in terms of lambda minus this. That's the resolve the calculation that we had from last page. Okay, so the rest is just tidying this thing to make it a little bit easier to read. So what I'm going to do is I'm going to multiply by 1, and my number 1 is going to be f0 divided by f0. Okay, so this is to tidy things up a little bit. Okay, and not only that, I will also divide by 1 over f on top and bottom, right? So I will multiply by another factor of 1, but my 1 this time is 1 over v, the speed of sound, divided by 1 over v like this. Okay, so you can see that in the end there's a few factor canceling out, and I just leave this as your exercise to confirm that what I'm writing next is correct. Okay, so v gonna cancel out. So what I want in the end is f0 in the top here, and then at the bottom I'm gonna have f0 times lambda divided by v, and then minus Vs divided by V. Okay, so that's a little bit of algebra. It might be a little bit complicated because of, like a lot of, 1 over divided by 1 over, but just try to confirm that this is true. And because V equal to F lambda, then this factor is actually just 1. Okay, so in the end what I have is F0 divided by 1 minus Vs divided by V. Okay, so let me summarize it here. So if the source is moving towards the observer, then the frequency heard by the observer is not just F0, but F0 divided by this additional factor, which is Vs divided by V. Okay. So what is Vf again? Vs is the velocity of the source, so how fast the source is moving. And V is the speed of sound. Okay. So you can see from this equation that if the source is moving towards the observer, F prime is actually larger than F. So you're going to hear the frequency actually higher than what it should be, because you're dividing with something which is less than 1. So you're going to hear higher pitch, essentially. Okay, so you can do the same thing to analyze the case where the source is moving away from the observer. So in this case, well, let me draw it here. So the siren of the ambulance is moving towards the observer. Okay, so you hear the pitch higher. But if it's the other way around, so if the source is moving away, then you can repeat the analysis. In this case, you're going to stretch the wavelength, so the wavelength becomes longer. So if the wavelength becomes longer, the frequency will become smaller. So in that case, what you have is f prime equal to f0 divided by 1 plus Vs divided by V. So in this case, F prime will be less than F0. So in this case, the ambulance is moving away from the observer. Okay, so the observer gonna hear the frequency to be a little bit lower, right? So you can see that the only difference here is you flip the sign of this thing, right? But the formula looks the same, right? So it's actually well, one thing that I probably suggest that if you don't remember if the sign should be positive or negative here, well, just think about what it should be in terms of the frequency, right? So hopefully you can trust your personal experience that if it's moving towards you, then the pitch should be higher, the frequency should be higher, so you need to divide by something lower. So it has to be a minus sign in that case. But if it's moving away, then it should be lower in frequency, then you should divide by something larger than 1. So it should be positive there. Okay, so the plus minus at the bottom here, I will just say that sometime if you don't remember, just make it, according to what you know from your daily experience. Okay, so let's maybe put in some number just to see how much it's gonna affect. Well, the normal siren, I mean, I'm not sure like what's the frequency, but the pitch is kind of high. So let's assume that normally the frequency of the siren is maybe 2000 hertz, right? And what happens if the ambulance is moving towards you with moderate speed? So what is moderate speed? Well, let's say it's moving at 60 kilometer per hour, right? And how would that change? Well, 60 is kind of probably not too fast, but it's also not too slow. So let's see. We need the speed of sound. The speed of sound, let's just assume that it's 330 meter per second. Okay. So in order to, use this formula, you have to make sure that V and Vs are in the same unit, right? So the first thing you probably need to do is to change this to meter per second. And I hope that all of you know how to do this, right? So it's going to be 60,000 meter divided by hour, right? So you need to make it something like this, so meter per second. Okay, so you're gonna have roughly about 16.7 meter per second. So that's how fast the source is moving, right? And now we know everything that we can put in the formula. So F prime is essentially just 2000, which is F0, divided by the factor that is related to the velocity of the source and velocity of sound. So this one, well, depends on what we want to calculate. Let's assume that it's moving towards you, right? So you need to divide by something less than 1 to make it higher frequency. So it's 1 minus Vs, which is 16.7 meter per second, divided by the speed of sound, which is 330 meter per second, right? So when you do this, what's gonna happen is that I gotta not punch in the whole equation first because I want you to see the factor down here. So the factor down here is gonna be about 0.94. Okay, so 0.94 is this whole thing. It's 1 minus that fraction. And you can see that it's less than 1, right? So it's gonna be, higher in frequency. So if you multiply this, you're gonna get the f prime frequency to be about 2100 hertz, or 2117 to be more precise, right? So you can see that the frequency is higher, not much, by about 5% compared to what you have earlier, right? But this 5% increase in the frequency is more than enough for our ear to notice, right? So actually, our ear is actually quite good in detecting change in the frequency, right? So something like this is easily observed in our daily life. Okay, so that's one case. Well, it seems like two cases, but it's actually just one, which is the source is moving, but the observer is not moving. We're gonna look at the other case. Okay, so let's talk about that. So the other case is when how did I write it? The source is moving. So the other case is when the observer is moving. And let's say the source is not moving. In the end, you can just combine the two cases together. So we don't need to do that at the same time. That's gonna make things overly complicated. So the observer is moving. So that means the ambulance in our case is moving with zero velocity. So Vs is equal to 0. And now the observer, which is here, let's say the observer start to move into the source itself, right? So we need another velocity to indicate that. So we're gonna use V0 here. So V0 is the velocity of the observer. Okay, and we're gonna assume that the observer move or run into the source. So it's moving to the left like this. Okay, so how does that change the frequency? The way we analyze this is a little bit different from what we had earlier. So what we had earlier is we look at how moving this, compress or stretch the wavelength. But in this case, the movement of the observer, what it changed is actually changed the apparent sound velocity. So it's a little bit different, and you probably think like, what's the difference? But I mean, it's a little bit subtle in the sense that you have to look whether the observer is moving relative to the air itself or not. The case we had before is the source moving, so the observer does not really move with respect to the air, which is the medium, right? So the speed of sound is always going to be v. But in this case, the source is not moving, it's the observer which is moving. So it looks like the speed of sound increased because from the point of view of you, it looks like the wind is blowing towards you, right? Because you are not standing still. The air is standing still. You are moving into the air. But from your point of view, it's the air moving towards you, right? So it's gonna carry the sound with a little bit more velocity. So that's kind of like the way I would think about. But in any case, if you're confused, then just think about it slowly. But just maybe believe me that the effect of V0 is to change the sound velocity. So the sound velocity V prime. So this is the sound velocity. What should I say? Sound velocity. Maybe it's the better way is to use it to say apparent sound velocity. Right? So it's the sound velocity kind of like seen by this observer, right? Because it's moving, so the sound velocity is gonna increase. Right? It's kind of like relative velocity if you remember from your physics 1, right? So you're moving, so what you observe is actually the sound moving faster than it did earlier. So the apparent sound velocity is the old sound velocity plus the velocity of the observer itself, right? So that's what's gonna change in this case. And this makes analysis a little bit easier compared to the previous case because in this case, f prime is simply v prime divided by lambda because lambda did not change, right? Lambda is the wavelength coming out from the ambulance, and the ambulance is not moving, so there's no stretching or compressing in terms of the wavelength. So you just divide by a regular lambda here. But now v prime is different than v, so we can have v plus v0 divided by lambda here. And then what we can do is we can rewrite this in terms of the frequency, and I'm not gonna do it too many steps here. I'm gonna write the result here, which is 1 plus v0 divided by v times f0. Okay, and just make sure that you know how to go from this to the end result here. Again, it's just dividing by f multiplying by f just to get here. All right. So the formula is a bit simpler because you don't have like, dividing by a large chunk of something, right? So in the end, what we have is f prime is equal to 1 plus v0 divided by v times f0 here. And you can see that the effect of v0, it makes this factor in front larger than 1, and then you multiply by the frequency, right? So in this case, f prime is going to be larger than f0 if you move towards the source, right? If you move away from the source, then you're going to flip the sign. So this is moving towards the source, and the next line is moving away from the source. And what's going to happen is you just flip the sign here. So in this case, f prime will be less than f0, right? And this one may be a little bit harder to observe in real life because you have to be the one that move, and that's a little bit less frequent compared to the source itself move. But that can also happen, right? So I don't know, like in what situation you're gonna be seeing something like this. But anyway, we have covered all the cases for Doppler effect. So now let's just combine everything. So we're gonna have like the most general case of the Doppler effect, where both the observer and the source are moving, right? So in that case, f prime gonna be 1. Again, plus minus depends on how the observer is moving. So we have this factor, and that's the factor coming from here that we just did, okay? And then if the source is also moving, you also need another factor from our previous case, like this, okay? So this is the most general case you can have, is when both the observer and the source are moving. Okay, so you need something like this. So how do you use this kind of formula? So let's look at an example again. So for example, we have like the ambulance, which is moving to the right. And then let's say Vs, which is the source velocity, is moving to the right with 10 meters per second. okay? And then you have the observer, and let's say the observer move into the source, right? So it's kind of like a head-on collision, probably not gonna end well for either parties, but let's assume this is the case. And f0, again, let's assume there's 2000 hertz, or maybe let's make it easier, just do a 1000 hertz. And the sound velocity, let's say, is 330 meters per second, right? So if you have like a problem like this, and then you are asked to calculate what is the frequency heard by the observer, right? So in this case, both the source and the observer are moving. So you have to look at the formula. The hardest part is to figure out what is the correct sign, okay? So in order to do that, I suggest that you do one by one, meaning that think about what happened to the frequency when the source is moving towards you. That's the denominator here, right? So it's gonna make the frequency higher, so you know to choose the minus sign, right? So f prime is something on the top, which we're gonna do it later, and then divide by the movement of the source, which is 1. It's gonna make the frequency lower, so you need the minus sign here. So 1 minus Vs, which is 10, divided by 330, okay? So again, the important thing is to choose the correct sign here. Now what about the numerator? Well, the numerator is the movement of the observer. So the observer moves towards the source. It's gonna make the sound frequency also higher, right? But because it's in the numerator, you need to choose a positive sign. So in the numerator, you have to choose 1 plus instead of minus, because you want to make the sound frequency even higher. So it's 1 plus, again, 10 divided by 330, like this. And then times f0, which is 1000 hertz. Okay? And then if we calculate this, so let me just punch in the number clearly. So 1 plus 10 divided by 330. So that's going to be 10, not 10, 1.03, roughly speaking, divided by, so the other one is minus, so it's going to be minus, roughly speaking, 9.97 times 1000 hertz. And in the end, you're going to have something like 1062, roughly speaking, hertz. Okay, so that's how we use this formula. And one interesting thing you can see here is that you can actually cancel the effect of the source velocity by moving away from the source itself, right? So if I change the situation such that the ambulance is moving to the right with v equal to 10, and then the observer is also running away from the ambulance with the same speed, like this, right? So we can use the same formula and then try to calculate the frequency. So you're gonna see that in this case, the factor actually gonna cancel out, because the difference here is you flip the sign of the velocity of the observer. So now it's gonna be minus, because moving away from the source is gonna make the frequency lower. So we need a minus sign in the numerator. So you're gonna have this, and then you divide by the same thing as before, right? So the denominator does not change. But you can see that now you cancel out what's gonna happen in front, right? Because it's just 1. So in the end, there's no change in the frequency, right? So if you run away as fast as the source is approaching you, then everything looks kind of the same. Yeah. Well, the source is the one that is giving out the sound, right? So that should be either the speaker or the, if we're talking about some, light wave is the light bulb or something. And the observer is anything that receive the wave, right? So in case of the sound wave, it's probably your ears, but it can be, you know, other detector or something like that, right? So I, by the context of the problem, it should be clear which one is the observer, which one is the source. Okay, but I mean, you can have like kind of crazy problems where one object is both the observer and the source, right? But we are not gonna do something like that. Okay, so okay, so that's how we do this kind of stuff, and it's not gonna be any more complicated in terms of like the problem involving Doppler effect. So most of the time it's just this formula here, and you just need to choose the correct sign. Again, that's the most important thing here, right? So if you're confused, then slow down and then think about what sign you should choose to make the frequency goes in the correct, um, direction, whether to increase or to decrease it. Okay. So next topic is the interference of waves. So that's gonna be a long topic. So I think what I'm gonna do is to maybe take a break. So let's do that, and then come back 10 minutes after this.